Today we're gonna do 5 at-home experiments that are very near and dear to my heart. And for the first time ever, we're sharing the recipe for our favorite bit of chemistry called elephant's toothpaste. We've got some epic science lined up, and the coolest thing is that all of them can be easily done at home yourself. Whoa, Bob, whoa. First up is my childhood favorite, the egg in a bottle experiment. All right, Science Bob Flugfelder. I did this at the science fair when I was in 1st grade. The main reason I liked it is because it involved fire.
Of course.
And I was allowed to light things on fire.
I'm impressed.
The ingredients for this experiment are very simple. We have an egg that's peeled, hard-boiled, just like a standard milk bottle you could order off the internet.
The neck size is very important though.
You want it to be just smaller than an egg. How do you get the egg into this jar? Because as you can see, it can't really work. It breaks the egg. That could have been a mistake. There we go. How do you get an egg into this jar without breaking the egg and making a mess like this?
What's the secret?
The secret, Bob, is fire. First off, goggle up for safety. I'm gonna grab these papers with tongs. I'm gonna light the paper, put it in the jar, put the egg on top. Look at that, a fully intact, non-broken egg is now inside this jar. When air heats up, the molecules wanna stretch out. They're moving around a lot. So when we light that fire, the air inside, it wants to stretch out. But as the flame goes out, that air starts to cool down. Then all the air molecules kind of suck back together, and it just pulls the egg right back into the jar. So now the question is, Bob, how do we get this out?
So you have to go from a vacuum to pressure.
We just blow into this jar, huh? Whoa! And there's our egg.
We should add a variable. A variable is something that you change. We have a water balloon. That's significantly bigger than the opening.
Again, if you're using fire, adult supervision is definitely required. Okay, that should get nice and hot. Oh. Now your challenge is to get that out, Bob. Oh my gosh.
That's all we get. I say we go one bigger.
Okay.
There we go. There it is. There's the blub blub.
Oh boy! Oh boy! Come on!
It's cooling.
Wow. Man, we're getting so close.
And we can't push it in either.
No.
We try.
Well,
wait.
Well, can we? Oh. That's even cooler. So that shows you just how much this air shrinks and expands when it gets hot, right? It's a good start, Bob. Next up is Bob's favorite experiment, slime. And here's why.
Here is a picture of me at 7 years old making my first ever batch of slime.
Aww.
That is my evil scientist face. A lot of people know how to make slime.
Yeah.
There's this old craft glue. The secret of this is a chemical called polyvinyl alcohol. Now, I add just a little touch of water. I'm just gonna thin that down a little bit. Let's mix that up. So this is still obviously very watery. The next, I've got borax. Now, borax you'd actually find in the cleaning aisle. I'm gonna take a teaspoon, 5 milliliters, and then we're gonna add about a half a cup of water. The nice thing about slime, everyone's slime is a little bit different,
That's
right?
cool.
So now we got glue and water, borax and water.
Yep.
Also important, you wanna add your color now.
I'm going Jello Pool Red, Bob.
I love the Jello pool.
How much of that should I do?
Not too much.
Why?
It's gonna get on your hands. Your hands will be red for the rest of the video. So you wanna add it to your glue solution.
2 drops?
Yeah, let's start off 2.
I'm doing 3, don't tell Bob.
I heard that.
Whoa, you're
very
just
happy
looking
with that.
Cool.
There are molecules in here and they're all loose. The borax is gonna bond all those together. You wanna just kind of experiment here. I'm gonna take maybe a teaspoon of this and you can see right away, look. Whoa.
I'm doing 3?
Whatever you want.
I'm doing 4, don't tell Bob. Okay, but mine's like kind of goopy and runny.
That means that you still don't have a lot of bonds that have bonded, so
I
you
see.
add a little more of the
I
borax.
need more bonding.
This is a bonding activity. All right?
Whoa!
So if you let it sit for just a little bit of time, it makes a difference, right?
It does. And I like how it doesn't like get on your hands. It seems like it would be sticky, but it's not. What if I were to add color now?
It would be very hard to mix in, right? Because all those bonds are made. Give it a try. My hypothesis is that Mark's hands are going to be blue the rest of the video.
Uh-oh.
They might be blue the rest of the week. That is cool. It looks like a blue heart.
I get why slime is so popular.
Yeah.
And I'm gonna go wash my hands. For at-home science experiment number 3, we've got a fun one that's pretty simple. You just take a very clean plate and just put a nice little layer of water. Have you ever seen those water spiders that like glide on top of the water? The question is like, why does it float on the water? And why doesn't it just sink? We're gonna demonstrate that a little bit while I just pour a lot of pepper. It's on the surface. It's like one of those water spiders. Okay, then you just take a little bit of this blue stuff we like to call dish soap, put a wee bit of it on your finger like so, put it wherever you want. I'm gonna go right in the center. I'm a magician! I am a powerful wizard!
Pepperus, Repellicus.
Whoa! You're a wizard, Bobby. What's happening here is dish soap has this special ability. It's called a surfactant. Surface tension is all the top layer of molecules in the water that are all joining arms. They're hanging together. Well, soap has this special ability to break those. As soon as you put soap, it rips that apart. And then almost like a rubber band, they all go to the side. And this is why dish soap is so good at cleaning things. That's what I love about science. It's like magic, but it's actually real.
For experiment number 4, it's super easy. For this, you need clear glass and,
Whoa, Bob, whoa.
So this is seltzer water. Put a couple of raisins in here. And you see how immediately we got bubbles released, right? All right, now put some of these popcorn kernels
So
in.
far, Bob, I'm not gonna lie, this is kind of a boring.
It's kind of lame, I get it. Now, we have our
They
dancing
float,
popcorn.
okay, they float.
But then,
Wait, what? What is going on? So clearly the bubbles that nucleate on it from the carbon dioxide, that's like arm floaties that are gonna float you to the top. And then when it gets exposed to the air, the arm floaties get popped, they sink, they get more arm floaties, they go to the top.
so I figured let's add a variable. Let's do it something taller, right?
I think there's no way a corn kernel will go all the way to the bottom. Okay, I'm dumping all these in with
try
my
it.
blue hands, which someone didn't warn me about. Whoa, it's like a race to the top. Oh, okay, halfway, 3/4. Oh, go. Yeah, we hit the bottom. This is actually way more impressive in a tall cylinder. This is like a corn lava lamp. Get out of here, Bob.
I don't know if it's gonna work. I haven't tried this.
My hypothesis is that we're gonna get one that goes all the way down.
I don't think so.
Go, 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 go.
No.
No! Come on, you got this. Oh, go, go, go! No! We're getting closer, dude. We're getting close. Oh! Yeah! This is what experimentation in science looks and feels like, you guys. We're just thinking of these things on the fly. We're curious, we're asking questions, and we answer the questions. One question we had was which of the 3 containers would keep the corn moving the longest? And spoiler alert, it was the biggest one, which had the most liquid and therefore the most carbon dioxide or bubbles stored up in the water.
It's time for experiment number 5.
Bob, what is it?
Elephant's toothpaste.
You guessed it. And this is an experiment, just like all these, that you should definitely be doing with a parent or some kind of adult.
So let's start with our hydrogen peroxide.
We're gonna do 6 ounces.
I want you to get 3 tablespoons of warm water. There we go. To that, we're gonna add 1 tablespoon of the dry yeast.
Okay.
Now I'm gonna have you mix that up.
Okay. It's a little like hydrophobic, or meaning it doesn't mix well with water unless you really try.
So while we let that kind of mix a little bit,
okay.
I'm gonna go with a good squirt of our dish soap, maybe like a tablespoon. And finally, some color, classic red. Okay, so let's review. In here, we have our hydrogen peroxide, liquid soap, and we have our coloring.
Yes.
In here, we've got our yeast and warm
Warm
water.
water.
And then the last step is to mix them together. Now this is gonna act as a catalyst. It's gonna speed up a reaction that's already happening. There we go.
Okay, ready?
Ready. Pouring, 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 pouring.
Whoa, here it comes, Bob. Wow, that's so smooth. It looks delicious.
Very laminar.
Oh, that's so beautiful. Whenever I smell this,
Yeah.
it brings back so many fond memories. Yeah, nerd hug.
Spent a lot of time with this thing.
In fact, for the first elephant's toothpaste we did in the pool, we ran so many experiments trying to get the right combinations. And we just weren't getting as much volume as I wanted. So I called up Science Bob.
Told me exactly what you're doing,
Yeah.
and you weren't using warm water.
It's the
Warm
one
water?
variable we weren't considering. Why do you think warm water does the trick?
Formula for water is,
H2O.
right, so here's my little model.
So this is your H, and that's your 2 O's?
Right, so you got H2O.
Got it.
With hydrogen peroxide, it's H2O2. And so we add a catalyst, and a catalyst tears the extra O apart. It hooks up with one of the other O's that pulled apart, and now we've got oxygen and water.
This is why you want the right amount of catalyst to pull these off. If you don't have enough, maybe only half of the hydrogen peroxide molecules get ripped off like this, right?
So many experiments. All right, so that was the at-home version.
That's right.
Now this is 30%, which is why we have got our goggles on, we have got our gloves on.
And for the first time ever, I'll say why Bob pours this in. In the video description, we are putting putting the recipe for this version of elephant toothpaste. The trick is you gotta do it with the science teacher, because only a science teacher will be able to get this 30% hydrogen peroxide. Plus, it is more dangerous, so.
Don't want to do it in your kitchen.
Or your bedroom.
What in the world? That's my office!
Okay, great. 3 tablespoons. Now we have soapy hydrogen peroxide.
In honor of elephant toothpaste 3.0, I say we do green.
I believe that got us a Guinness World Record. And now our catalyst is no longer yeast.
Yes.
We're using a chemical called potassium iodide.
Your science teacher will get easy access to it.
We saw the home version. Let's do the television version.
Television version, here we go.
I'm gonna give you the honors. There it is.
And you step back. We had discussed moving it away from the camera. Here we go. Uh-oh,
Here
Bob.
comes the big one. Whoa!
It is definitely warm.
Yes, this is an exothermic reaction, which means it gives off heat. Definitely don't want to touch this foam.
Yeah.
And you also notice that it's got these brown highlights.
what's up with that?
So that's the iodine from the potassium iodide, which is brown. Let's add one more variable just to see what happens.
Okay.
Version 3, again, we're just adding a variable.
And ideally, you just change one variable. In science, the reason you change just one variable is now if the result is different, you know it's because of that variable. If you change 3 at a time, the result will be different. You don't know which caused it. If this looks different, we know it's because of the container. We are using glued food coloring because we haven't used glue yet.
Same catalyst, same amount. And it goes.
I was not expecting that.
Wow.
It just plopped out, Bob.
And a lovely blue coloring. We got our gloves on, but it's still hot. I can feel the heat on that.
It was, ooh, yeah, that's really warm. Even through the gloves, you can feel the warmth.
So even if you do a home version, find a variable and experiment.
And change it and get it to look as cool as possible. The most important words in science aren't eureka, it's that's interesting. Because you do something, you're like, whoa, I wasn't expecting that. So let us know in the comments what experiments you want to see us do next. If you try them yourself, of course, tag us on our socials at Crunch Labs. We'll catch you next time, right here at Crunch Labs.